Okay, well, this talk is based on a talk that my friend Martin van der Mark gave at a San Diego conference in 2015. I've modified it fairly extensively, added some things in, taken some things out, but it's based on that talk, and it's going to be on a couple of stuff. One is on the nature of stuff. What is everything made of? What's the world around us made of? Asking some very general questions about that, and giving some possible answers to it as well later in the talk. But it's also going to be about something else. I'm also going to talk about the hierarchy of forces. The hierarchy of forces, there are a set of forces in nature. Gravitation is the weakest one. And then one has in the standard model, in order of strength, electromagnetic, with electro being weaker than magnetic. Electromagnetic, the weak interaction, and the strong interaction, or the electro-weak interaction, if you like. The two are related inside the standard model. But there's a hierarchy of those forces. One might think that the strongest force is the one that talks to, that appears first, but it's not. It's the weakest force that is the one that has to intermediate between things eventually. And the reason for that is that the strong force is a very strong force, and what it does, it satisfies itself as much as it can. And once that force has satisfied itself, has done whatever it needs to do, then the next force down in the hierarchy is the one that then has a go at satisfying itself, and all of those things happen up until the point where they're left with the weakest of them all, which has to, or the weakest of all of the ones in a particular kind of interaction, which then has to intermediate with the outside world. We'll talk about that in more detail later in the second half of the talk. So let me just see if I can change this here. So the first part of the talk is the nature of stuff, and the second part will be the hierarchy of forces. So the nature of stuff. So what is the matter that forms the world around us and forms the universe we live in and forms ourselves? So what is everything made of? Now, quite a reasonable answer to this might seem to be that it's either matter or light. We have matter, material systems, electrons, protons, neutrons mostly, and otherwise the interaction between them, the things that we see and the things we touch, taste, smell, the senses we have, they're all intermediated by electromagnetic interactions in the worldview that we have in the 21st century at any rate. So really the kind of things we'll be looking at are matter and light. So for the purpose of this paper, we're only actually going to indirectly a little bit talk about the latter possibility, but I will come into that. So what is this matter, this material substance? And what is the ultimate substance? What is stuff made of? What are electrons, protons, neutrons, all the elementary particles? What are they made of? Is there a primordial stuff of which they're all made? And then for that primordial stuff that exists, is it massive? Is the mass arising from that stuff or from something else? And as a consequence of this mass, this possible mass that may exist in this stuff, does it contain or possess energy, this stuff? Whatever this primordial stuff is it penetrable? Does it exert a force on things? Is it something which can be perceived? And the last question certainly has a bearing on the nature of radiation, which is penetrable. It can go through things, go through glass, it contains energy, clearly, light contains energy, and it can exert a force on matter. If it hits something, is absorbed by something or reflected off something, then it has a momentum transfer to that thing, which is given by its energy divided by C. So certainly light has a force associated with the electromagnetic force. Now, before I start, I want to say which framework I'm going to use, as well as talking about stuff. And one of the things I'm going to assume is that energy is conserved, that whatever energy, different forms of energy can perhaps transmute or transform into one another, but that energy is conserved. And I'm going to only consider places where it's conserved locally. Now, this is locally in the quantum sense of local stuff. We're not losing or gaining things from a system which is under observation, which can happen. You can have a non-local conservation of energy. If you have something which is emitting photons, they go off somewhere else, and the body has lost energy. But we're going to consider only stuff where the energy where we look at the whole system. You can do this with light as well. You just make the whole system bigger and put the beginning and the end of the photon within the same system. That's also local in the sense that light transforms the nature of space and time to bring everything local, because at light speed, everything's at the same point in space-time. So we're only going to consider a locally conserved system, but that isn't really much of a limitation because pretty much everything can be put into that frame if we choose the proper frame of reference. So we're going to consider only closed systems so that we can talk about energy balance and the conservation of energy. And we're also going to consider that E equals mc squared for any kind of energy, whether that energy is something we're thinking about, or even if we can't think about it, if it's something like dark matter, which hasn't yet been detected as to what it is experimentally, but one can still, even if it's unthinkable in terms of what it is, if it contains energy, we're going to say that thing contains mass as well. This is setting up the framework of what we're going to assume. But the energy of the meaning of Einstein's famous E equals mc squared equation is that energy is equivalent to mass and not another form of mass. Energy and mass are equivalent. So it's not a transmutation equation. It's not a process equation. It's not saying that energy can transform to matter and matter can transform to energy. It's saying that energy is mass. And if you want a proper explanation of this, then have a look at Light is Heavy. Van der Mark and Toft wrote a paper on this some time ago, and there's also a more recent paper talking about that, a 2019 paper, which we'll get a reference for later. So what we're going to assume is that if we put any kind of energy on a balance, so if we have a box and we fill it with all sorts of stuff, we fill it with whatever, photons, with interactions that have energy, they can be positive or negative. Of course, you can have attractive energy, which is a negative mass, or mc squared, some mass, or whatever. All of those things, if they're confined within a system, amount to some mass which can be measured on a scale. That's the assumption. So let's think fundamentally about stuff in the abstract. So imagine that some stuff does exist, but never exerts any kind of force whatsoever on any material. Nothing ever happens. We can't know that stuff exists at all. And then it's effectively not part of our world. So that would be a kind of invisible stuff. Is there any sort of invisible stuff? And the answer is going to be no, and I'll tell you why. If it did have some kind of interaction in its own invisible world, somewhere else, another space, another time, whatever, the force is a gradient of some energy, it would then, if it possessed energy, become part of our world, at least through gravitation, because it then has a mass associated E over c squared with that energy. And so we could observe it in terms of the gravitational effect of that material. So that means that it isn't, so by the assumption that we've made about the nature of energy, then such things do interact with our world. So that all of this, anything that has energy does exist in our world, even if it's only via the gravitational interaction, the very weakest of the weak interactions. So let's look at the consequence of this. This means that any stuff to be useful, it must interact in some world and must therefore have some energy. In other words, stuff can't be truly sterile in the fact that it has no interaction at all with our world. Otherwise, it is out of this world quite literally and not interacting. Conversely, it also implies that anything at all that exists in the universe must have energy. And finally, we can conclude there's only a single world and that it contains everything that exists, and that is our universe, whatever that is. And that universe is what we're trying to understand both here and elsewhere, and as humanity. So one has to conclude from this little discussion that energy is part of stuff or is some form of stuff. And this raises more questions. What is that fundamental stuff? Is there more than one type of stuff? Do we have stuff and anti-stuff? Do we have different colors of stuff, stuff that interacts in different ways with itself elsewhere, or what? Are the things that we're talking about in terms of our standard model, things like charge or quantum spin? Spin has energy. Quarks, do quarks are they some kind of stuff, some sort of fundamental stuff? And this fundamental stuff, whatever it is, or fundamental stuffs, are they quantized or are they continuous? So do we have something which is like a fluid of some sort, a division that can be ultimately divided down, 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 down as far as you like, absolutely continuously? Or at some stage does it come down to some point where it's necessarily quantized? It's a question that we're going to be addressing. So what we're going to do is look at different special cases of what stuff could be, and then have a look at the logical consequences of that, and within our framework, where we've assumed conservation of energy, of course, as our absolute framework. So, and then go through whether that kind of stuff can or cannot be. And we'll quite quickly come down to the nature of stuffs that can exist within the framework that we've set up and stuff that can't. And some of the things that can't are things that people think can. And I'm going to try and prove that they can't. So we'll see how far that goes and what sort of reaction it gets eventually when this stuff comes up on the web. But there we go. That's what I'm going to try and do. So let's start with transformation or transmutation of energy to mass and vice versa. So we're thinking about physical processes which are observed in nature, such as the annihilation of the singlet state of parapositronium. Now, there are two kinds of positronium. Positronium is a hydrogen atom, except not with a proton and electron, a proto-electron, but with an electron and a positron. They form a bound state, and this stuff has been formed in the lab, and such states decay, and they decay in two ways, pretty much, not entirely, but pretty much. You have, if you have parapositronium, where the spins are anti-parallel, this is anti-parallel spin case, you have a singlet state, you have a spin zero state, and those things pretty much always decay into two oppositely directed gamma rays. So E plus E minus goes to two gammas. If you make orthopositronium, which is the triplet state, spin one state, then that decays pretty much exclusively, though not entirely, to three gammas. Now this is evidence that gammas carry off one unit of angular momentum, because if you've got spin half parallel, you've got spin one. That gives you three gammas. What happens is two photons go off and they carry off plus and minus momentum. They have the same circular polarization traveling in opposite directions. And the remaining spin is carried by a third photon, 3-photon decay for orthopositronium and 2-photon decay for parapositronium. So energy is conserved. If we have a positronium at rest, it's only got its rest mass, and then you get two gammas of 0.511 MeV each, exactly the mass energy of the electron. E mass electron gives me mc squared worth of energy. E is h nu for the two photons. So the total rest mass of the electron is transformed to two photons. So this is an experimental thing that just happens. Now the reaction's assumed to be reversible, but it's hard to carry out. Hitting two photons precisely dead on is hard enough if you don't have to make them into gammas, and gammas are notoriously hard to steer. So it's presumed that E plus E minus goes to two gammas, but also the reverse process happens, that two gammas can go to E plus E minus. But normally, if you're doing an experiment, a high-energy physics experiment, where you produce dozens or thousands of these things, when I was working at CERN, my responsibility was for an electromagnetic calorimeter, where very high-energy electrons would come in, form electron-positron pairs, which would go to gammas. The gammas would form electron-positron pairs, forming a cascade of particle-antiparticle pairs, which went all the way down the energy scale until they had too little energy left and they stopped forming electron-positron pairs. But you got hundreds of these things, and you always do in these. This is a normal process in any kind of high-energy physics experiment. So what you normally have is you have a gamma plus an atom, or a gamma hitting some other elementary particle, spalling off it, produce an electron-positron pair. So that's what happens there. Now, this pretty much is a total transformation in the forward process, where you have parapositronium going into radiation. There's a complete transmutation of massive systems into electromagnetic radiation. Now, if one were to look at a quantum mechanics to be developed, where you could have the continuous transformation of matter into energy, that implies that the stuff that you're talking about inside those equations to be developed, because electromagnetism as it stands doesn't have that, and also the standard model doesn't have that process. In quantum electrodynamics, you just presume it happens. You don't have a development of a wave function going from one to the other. Although if you have looked at some of my talks on Quicycle, you'll see that that within the new theory, the extended Dirac-Maxwell theory that I've developed, that one does have such a process. So there one does. So this has been a new development since 2014. But in any event, experimentally, there is a transformation of pure matter to pure energy. Then that would suggest at first instance, and that there is no different stuff in that process than the electromagnetic fields. So that's what you have in the end state. And if you can describe it as purely electromagnetic in the end state and have some quantum process by which that happened, then really it should have just been a transformation of purely electric to purely electromagnetic in a different configuration. So if they were purely electromagnetic to begin with, they could radiate purely electromagnetically. Either that, or there is another kind of stuff which leads to both, a deeper level than both light and matter, which can form, for which one can have some sort of wave function which describes matter in one way and then describes light in another way. So now, if there is just one kind of stuff, bringing together twice the amount, it should make it disappear. So it's not completely vanishing. So it's not stuff and anti-stuff. Electron and positron are not opposite kinds of stuff, because are not opposite in the mathematical sense, +1, -1, because it's not disappearing, it's turning to energy. So one would think that the stuff is at least partly electromagnetic. The stuff of the electron or the positron is at least partly electromagnetic. And of course it is, because if you look at an electron, it's got an electric field, and that's electromagnetic. So it's also got a magnetic moment, that's magnetic. So experimentally also, electrons are at least partly electromagnetic, just experimentally and also in the standard model. So what we could say here is we could say that stuff in this sense, for both electron stuff, positron stuff, and light stuff, is either a form of electromagnetism or a form of extended electromagnetism. So that's one possible special case of stuff. Let's have a look at some more. So let's talk further about this stuff being its own anti-stuff. So particles can have antiparticles. So if stuff was continuous, one could have any amount of it. So if it was own anti-stuff, you'd just, what would it be going to? Stuff, anti-stuff can't go to no stuff at all and conserve energy, given that stuff contains energy. So if stuff is quantized, only one quantum can exist, and each fundamental particle contains a quantum of some set of quantum numbers, in fact. But it contains a quantized amount of this stuff. Electron has a particular mass. So if that's so, we know there are different particles. There are protons. They're different. They're much bigger, 1,800 times as big. So what is it that makes these things different? Or equivalently, what properties can you give to this that may be imposed by the boundary conditions in any theory one makes for this? Imposed by space, time, energy, the things that we're assuming exist in the boundary of this talk. That quantization, where does it come from? Where does quantization come from? Well, in a quantum theory, one often puts it in as a quantum condition on a commutator is equal to something to do with h bar d by dt. You have a commutator of something with the Hamiltonian is equal to ih bar d by dt. You're inserting a quantization in there, imposing quantization. But what is quantization really? Quantization really is something that a particle forms to naturally in terms of coming back upon itself and reforming itself and self-creating itself in some continuous way. And we're going to come on to thinking about how that might be the case later. So you can get quantization from periodic boundary conditions. If something goes, well, just philosophically, if something goes round and round in circles and recreates itself on every turn, then you have a self-creating system. You have a system which is at least maintaining itself. Now, if those systems can interact elsewhere and they're all the same, they can interact, one's got more energy than another, they can interact with one another, they are interacting away and they equalize their energy. So if you've got things that are doing this and they can interact, they will thermodynamically equilibrate with one another quite rapidly, because we're talking about elementary particles. The elementary vibration frequency is 10 to the 21 hertz. The mutual interaction rate is roughly the fine structure constant, which is 100 of that, which is only 10 to the 19 hertz. That's quite a fast interaction rate. So if you had an electron that had a bit more or a bit less energy, it would very quickly, and had a particular topology, same topology as all other electrons, then these things would interact amongst each other in such a way that they all had the same energy locally. I'm assuming everything's local, so that's the whole universe for you then, so in terms of light. So the quantization of mass can come from a topological situation, which is the same for all these particles, which are interacting. So But it's going to become clear later in this talk that stuff has to be continuous. Whatever the underlying stuff is that electrons and protons and all the other particles in the universe are made of, it has to be continuous. It can be quantized by this condition of making it go around and around in circles, so it can be counted. Quantization just means counting, but it has to be continuous. I hope that becomes clear. So if there's stuff and anti-stuff, and the sort of, or stuff thing and anti-thing, positron, electron, can be brought together to annihilate into another kind of, or another form of this stuff, radiation. So there are a couple of, if one wants to separate those two out, that means there are a couple of things which both couple to electromagnetism. So what is it that's carrying this anti-property there, if you're talking about coupling of stuff to other stuff by electromagnetism in terms of the theory, which is part of the model of quantum electrodynamics, where the basic interaction is a charge system emits and forms a photon, which then interacts with the charge system. And there's a probability for one emitting and a probability for one absorbing, and the mutual probability is a well-known number, and the rest is just geometry. So quantum electrodynamics is really quite simple, although the maths can look anything but simple, of course. But what is the thing that's carrying the anti-property in this electron or proton? One thing you could go for is you could say, okay, well, could it be charge? Because for electron-positron, you've got plus charge for the positron, minus charge for the electron. So there's a possible anti-property. This could be something which is, stuff could be charged, except photons aren't charged. But okay, we'll come to that. So it could, charge conjugation is an accepted particle-antiparticle transformation thing. It's one of the things that are cancelled in annihilation. Spin's another one. There are a set of these things, lepton number in the case of electron-positron in the standard model. So, but charge is an electromagnetic property. It's something which is there in Maxwell's equations, added to Maxwell's equations by hand, right enough, but nonetheless there in Maxwell's equations. And it's apparently intimately connected with whatever stuff is, because electrons and protons have charge, and matter consists of charged particles. So, and of course, the bit that isn't charged, the photon, is purely electromagnetic. So, but then photons don't exist unless they're emitted or emitted by charged systems. So, intimately connected to stuff indeed. But another possibility is you could go by the CPT theorem, charge conjugation, parity, inversion of space, time, reversal. Now, for any process that exists in nature, experimentally, there is an equivalent. There is equivalent process if one imposes those three conditions, CPT. So, and that include that. So, for a process in the material world, there is an equivalent process in the antimatter world, provided that you impose both charge conjugation, parity reversal, and time reversal. So miss out any one of those and it's not allowed. So the anti-stuff, whatever it is, in terms of, has opposite-handedness, or it can be thought of as running backwards in time also. All three of them, charge swapped, running backwards in time, swap the handedness. So, or at least do the inversion through a point, which is what parity is. It's not just quite as simple as handedness, but okay. But this is going to require the stuff to be really quite a lot more complicated than kind of just basic sort of scalar stuff. So that would mean that space-time, or whatever this stuff is in space-time, must itself have a non-trivial structure. And that's certainly a possibility, which is always part of the nature. But as you attribute more and more properties to this stuff, it becomes less and less fundamental. And that's not what we'd like. I mean, if you look at what's thought to be the fundamental stuff in quantum field theory, you're talking about some vibrating string. If you look at the mathematics of that string, that's an incredibly complex thing all by itself. And especially when that's something which has never been observed, then you're starting with something extremely complicated that you've made up that's never been observed. Good starting point, but not a good starting point. So you start getting some very complicated things in terms of what people believe at the moment, widely, are the basic things of which the universe are made. Now, I think that's complete nonsense to go to something that complex, and I'm going to try and show that it can be a lot more simple than that. So, because then we're sort of talking about a meta stuff. We're talking about stuff which is conditioned, which is really a quantum wave function on on a membrane or in a string with lots of properties, SU3, SU3 of color, SU3 of flavor, SU2, SU1, U1, cross all those things together, enormously complicated thing. And then you start with that and that's basic. Well, I don't think so. So I think it immediately begs the question of how did that work? But nonetheless, a further question comes to mind. If there is some primordial stuff at which these things are made, how does it know where the electric charge of the electron is, or where it's going, or if it has no interaction with that, is it at least as strong as the electromagnetic interaction, or is it stronger? Does it have to be stronger? It does have to be stronger. But to solve this issue, material stuff must be coupled to something else. It must be coupled to electromagnetic, certainly, maybe the weak force, possibly the strong force. It can't just be as dull as galactic dark matter. Gravitation's much too weak. If you've got an electromagnetic particle and you start bashing it with stuff, gravitation's far too weak to keep up with a charged particle and confine it. It's being pulled by another charge, let alone anything else. Just speeding an electron up and down an aerial is already too much for gravity. Now, okay, so that's where I've got to at the moment. That's the first part of the talk, talking about general properties of stuff. So I'd like to go to questions. So we could stop recording. I'm the one who's recording, aren't I? How do I stop recording?
Don't stop recording, John. Keep the recording going for the Q&A.
Let's do the Q&A. Let's go for it. So I'll open. Everybody can stick their microphones on as they like. If they want to ask a question, make sure your microphone's on, and I'll do my best to answer it. Any comments or questions welcome at this stage.
Oh.
Roger.
I have no questions so far. It seems very coherent to me. And I hate to say it, but I agree with everything you've said.
My goodness.
That's shocking. How is that possible?
To ask a question?
Yeah, please do.
Looking on page 12,
Yep.
the line that says, how does stuff know where the electric charge of the electron is and where is it going? Now, my understanding of quantum mechanics is that these things are not known, so they're all dealt with in terms of probability. Is that correct?
That's exactly correct. Do you want me to comment on that and say, you know, what we've done so far is the stuff that I've put up here as a framework to this is pretty much conservation of energy and space and time and nothing else. It's all been general. So, and of course but as soon as you get to quantum mechanics, you know, quantum mechanics is a bit mystical these days because you have this stuff where you have this uncertainty relation. You have the uncertainty relation and you cannot, and there's these statements made, one cannot know the position and the momentum or the energy and the time of a particle precisely by making a measurement. And that's true if that's all you know, if you just make one measurement. But you know, in the actual physics of looking at material particles, which I've spent a lot of my life measuring and writing papers on, it doesn't really work like that, you know. These things in high-energy physics, they're very well localized. You know exactly where, with respect to a proton and a muon hit it, or an elementary particle hit it, because that's localized 10 to the minus 15 meters. And then the energy is utterly enormous, and the energy is also precisely measured. The uncertainty relation is out of the window for that kind of process, because you know much more. You're not making just one measurement. You've also got the measurements of the thing coming in and going out, and you have a whole picture in which that's embedded. Now, quantum mechanics has become mystical, especially through the Copenhagen interpretation of quantum mechanics. But what we need to do is not, if you start with a principle, there are certain things you cannot know, as you do in quantum mechanics in the textbooks, then one can be absolutely sure that there are certain things that one is not going to know. And you know, starting there with that kind of thing at a beginning principle means that you already know you don't know stuff. So, and then putting that on as a principle means that you know, going from there, this is not the best place to start from. In Dutch, there's a phrase that says, if somebody doesn't know what the hell's going on, die mensen gaan de mist in. They go into the mist. Now, in Scottish, we don't spell mist with an I, we spell it with a Y, M-Y-S-T, and that's the root of mystified and mysticism and mystic. So now,
Ah,
Roger. So I don't go there. I'm looking inside quantum mechanics. I want to know how it works and why it does what it does. And actually, I've got a talk up which I'm preparing at the moment, which talks precisely about that process of quantum collapse and why it's not mystical. So that's going to come in a few weeks' time. In the process of writing it at the moment, it's new talk. So that's something that's going to come up. But yes, you're right. In terms of quantum mechanics, one has a problem, but one doesn't have to think only in terms of non-relativistic quantum mechanics. One can think in other terms too. And
I have another question, John.
Don, go for it.
In your bottom line, does quantum mechanics seem to you to be an absolute authority on what's happening?
No, quantum mechanics is an approximate theory. And relativistic quantum mechanics, Dirac's relativistic quantum mechanics contains, Dirac's one of my heroes. But it took me quite a long time to thoroughly understand relativistic quantum mechanics about 20 years ago. But and it was about 5 years ago when I began to find where he was going wrong. And that's why the new theory, in the other talks I put up, I am claiming are the Dirac equation as it should always have been. And that goes inside the electron and inside quantum mechanics and derives the uncertainty principle, doesn't put it in as a principle. And,
what do you call your theory?
A new theory of light.
New theory. I like it. Got to write that down.
It's up on the talks on Quicycle. There's a bunch of them. So title things like the theory of light and matter, or I suppose
quantum bicycle.
Yeah, quantum. It's Quicycle.com. If you go to Quicycle.com, there's how many videos have we got up now, Arnie? I don't know. It's dozens anyway, but and there's 4 or 5 of mine.
Okay.
Including the stuff on that. But I'm going to come to it. I've got a slide down here that does it. So in one slide. So I'll show you the new theory in a minute.
So your bottom statement is suggesting that on the cosmic scale of things, we need to be looking at the electromagnetic aspect being a greater force than gravitation.
Oh, it is much greater. It's 10 to the 39 or 10 to the 42, depending on whether you look at electrons or protons, times bigger.
So to understand how the cosmos works, we need to be looking at it from the electromagnetic point of view more than gravitation. Is that true?
No, and that's what I'm going to talk about next, is over the hierarchy of forces, because really the thing is that electromagnetism will satisfy as far as it can over gravitation, and one can be left with purely neutral systems which are only gravitational. However, on the other hand, yes, absolutely, electromagnetic force must also act on a cosmic scale, and it is scalable. It scales from very, very big down to extremely small, small as you like to go. Virtual photons in high energy physics experiments are 10 to the minus 18 meters. The universe is 13.7 billion light years in radius. So yeah, all the way up, all the way down, electromagnetic forces operate. These things, as far as we know, I mean, they might not. I mean, they could get tired or whatever. And but you know, to a very good approximation, electromagnetism goes at least as far as gravity, possibly even further. And it is much stronger, but it usually tries to be in balance with itself. So as soon as it's in balance, and it has to be in very nearly perfect balance for it not to dominate over gravity, because your 39 orders of magnitude are quite a lot of zeros. So, so yes, I think, and we think, Marnie and I believe, and Quicycle Group believes, that electromagnetism is something which is enormously neglected in cosmology. So yes.
Yeah. Okay.
John, if I may, just a point of clarification, something that just came to me now while you were describing the E plus and the E minus. So since the magnetic force is stronger than the electric force, and since an electron and a positron both have their north up, but they have opposite spin, when they approach each other, doesn't mean that their magnetism will attract more strongly than their charge, so they're going to align the north to the south pole, which puts the magnetic fields opposite, which forces the cancellation?
Yeah, well, that's spin up and spin down. So no, but the spin up and spin downness of the positron and the electron. Ah, yes, I see what you're thinking, but no, I think the electron and the positron inside are really one's talking more about spin here and about the you've got a total cancellation of everything in terms of electron and positron. They have opposite scalar part. They have opposite spin in the parapositronium case. They have opposite charge in the parapositronium case. So you're right about the north poles and so forth, but remember that the poles do not appear unless the thing is sitting in an external field, an external magnetic field. And what's happening is the field's spins opposite. You're thinking in terms of a spinning charge. I don't think that's the right way to think about it. Not at the level of the overlap of the fields.
Because these things are tumbling and moving in 3 dimensions in such a way that it's not static.
Exactly. And the spin is the internal spin.
It's really more about the flow within the particle that has that opposite chirality.
Well, remember that the positronium is not an electron positron really. It's not an electron and a positron. It's an electropositron. So the thing's sitting in a resonant harmonic motion with respect to the positron part and the electron part. Now they're opposite in every way. And the remarkable thing is, of course, that these things go around very many times. The decay time is not short, it's minutes. So it's not it's a complete match, not very often. Anyway, but yeah, that's something we're thinking about.
Talking about when they paired up. I guess I was thinking more when they approach each other and collide. But I suppose the point is still the same when you're making about the topology of the particles.
Right. It is the same. It is the same.
Okay.
Remember, they're also attracting one another. But there's no, the cross section for that annihilation is quite large. It's quite a likely event compared to hitting a proton or something like that. Protons are much smaller.
So you're saying they're attracted into the annihilation? I mean, they're oppositely charged, so it makes sense.
Well, that's right. But remember, there's no dissipation. So a comet coming in isn't attracted into the sun. So in that shape, in that event, not. But in my view, these are both really confined mass photon systems. So as they begin to interact with each other, they're both vibrating extremely quickly, and they're interacting with one another not just in the electric field, but also in the overlap of their actual fields, of their internal fields. That begins to play a role, and they have the same frequency as each other. They're both vibrating equally quickly. So that is going to form a very strong quantum interference pattern, and it's going to look for the possibility of those things forming annihilation. I think the annihilation is more likely when you move them towards each other. When they get into the resonant harmonic parapositronium system, that has a long lifetime. That's quite nice. Something has to disturb it a little bit to click it into annihilating, I think, just thinking about it. But that's beyond the danger is here. We've got a long way beyond the scope of this talk. That's a very interesting question. You're right. We'll have to have a proper think about it at some stage. Good question, though, Arnie.